Now, the next thing we're going to be looking at is a compound event that is independent of each other. This is the first one we're looking at. Two events are independent if knowing that one will occur or has occurred does not change the probability that the other occurs. Now, the biggest change for what we're doing here is we're doing compound events. These are when more than one thing is happening. This is going to happen, and then this is going to happen. So I like to call these the and then problems. Okay, it's not a typical and problem where it meets two criteria. This is the and then problems. It's two things that are happening. This is happening, and then this is happening. For independent events, this is where one thing does not affect the other. Okay, they are independent of each other. The probability that a coin toss results in tails, given that the last flip was a heads. So when you flip a coin, when you flip it the first time and you get a tails, when you go to flip it again, it doesn't matter what you got last time. It's not going to affect what you get this time. Each time you flip a coin, it doesn't matter what you've gotten last time. It's never going to change what you get the next time. That's why we say those are independent. Another example of that might be rolling a dice. If you roll a die and get a 5, it doesn't matter that's not going to affect what you get next time. It's all just a random chance every single time. Dependent, on the other hand, this is two events that are dependent if knowing that one will occur or has occurred does change the probability that others occur. This is, for example, the probability of drawing a 2 of hearts given your first attempt was a 5 of clubs without replacement. So this is talking about drawing cards from a deck of cards, a regular playing cards. Okay. If you take one of the cards out of the deck of cards, you have now changed the deck of cards. By changing the deck of cards, you have now changed the probabilities of all the remaining cards. If I take a red card out of the deck of cards, there are now less red cards in the deck of cards. So that changes the probability of drawing a red card. It also changes the probability of drawing a black card. So these are dependent events. Having one happen will change the probability of all the resulting events. That is dependent. Independent, they don't affect each other. That's like rolling a die, flipping a coin. Rule number 2, law of independence. Multiplication for and this is intersection. That's what this kind of upside down U. It's kind of an intersection. We can use it to make an N, so we call it intersection. Okay, and this is the and rule. This is the and then rule. Again, this is two events that are happening. Right, so down here for number 5A, if two events A and B are independent, that is, one does not affect the other at all as far as their probabilities are concerned. Rolling a die, flipping a coin. The probability of A and then B occurring, so the probability of A and B is equal to the probability of A times B. So in this case, we are multiplying the probabilities together. For the or, we added the probabilities. For the and, or in this case, I like to call them and then problems, we are multiplying the probabilities together. For the two events, you multiply the probabilities together. So this is if they are independent, find the probability of A, find the probability of B, multiply them together, no problem. For part B, this says if two events A and B are dependent, the probability of A and B. So we're looking at the probability of A intersection B is equal to the probability of A. It's still multiplied by the probability of B. However, the probability of B, we have to be careful. This says the probability of B given A. That is the probability of B taking in account that A has already occurred. If I take a card out of the deck of cards, there's now one less card in the deck of cards. If I took out a red one, there's now one less red one. So all this is saying is when you go to find the probability for B here, just be careful. Adjust the probability based on how having A occurred has changed the situation. Number 7. A certain brand of firecracker claims that it will go off 95% of the time. If you buy 3 firecrackers, what is the probability they will all go off? assume that they are independent of each other. S is a successful pop, so the probability of S is the probability the firework will pop. Okay, so here, if we look at that, if I want to pop all 3 firecrackers and I want them all to go off, that is the probability of getting a success and a success and a success. Okay, so since they are independent, that means that I should just be able to multiply their probabilities together. That is the probability of a success times the probability of a success times the probability of a success. Right? The probability of a success says up here that is 95% of the time they will pop. So 95% changed back to a decimal form is 0.95. So that's 0.95 times 0.95 times 0.95. That gives us a probability of 0.857375 if you just typed it into your calculator. So we'll go ahead and round that off to 2 decimal places. So the probability of 3 fireworks going off in succession would be 0.86. Number 8, find the probability of drawing a king of diamonds, replacing it, putting it back in the deck, and then drawing a 5 of hearts from a deck of cards. Now, if you're not familiar with a deck of cards, there's a little note here. It says, in a standard deck, there are 52 cards in all. So in a standard deck of playing cards that you play poker or some other game with, there are 52 cards in all. There is only 1 king of diamonds in that deck. There is only 1 5 of hearts in that deck. Okay? There are diamonds, clubs, hearts, and spades, but for the king of diamonds, there's only 1. For the 5 of hearts, there's only 1. And since we are putting the cards back, when I take that king out, look at it, yeah, I got it. I put it back. I've now reset the deck, so nothing's changed as far as the deck is concerned. So that's why we consider these independent, because this is with replacement. So if I want the probability of king of diamonds and a 5 of hearts, since these are independent, I just got to multiply the 2 probabilities together. So the probability of getting that king of diamonds first and then getting a 5 of hearts second. Okay, since there are 52 cards in all and there's only 1 of each of those, the probability of getting a king of diamonds is 1 out of 52. The probability of getting a 5 of hearts is again 1 out of 52 because there's only 1 of those in that deck of cards. So 1 out of 52 times 1 out of 52 gives us a grand total of 1 out of 2,704. So now we're going to find the probability of drawing a 2 of clubs, set it aside, and then drawing a 3 of hearts from a deck of cards. Note again, there is only 1 of each of these cards in a deck of cards. Okay, so again, all the cards in a deck of cards are unique. There's only 1 of each of these. Now the biggest change here is that when I take out that 2 of clubs, I'm going to set it aside. When I set it aside, when I take out that 2 of clubs and set it aside, when I go for that 3 of hearts now, the deck is no longer the same. It has been changed by the fact that we took out the 2 of clubs. So drawing that 3 of hearts is dependent on the fact that I've already taken out a 2 of clubs. So that's why we say this one is a dependent situation. So when I multiply these 2 together, I have to take into account for that 3 of hearts the fact that I've already taken out a 2 of clubs. So when I will look at this one, I got the probability of the 2 of clubs times the probability of a 3 of hearts given the 2 of clubs is already taken out. So how does that change the probability? Well, for the 2 of clubs, there's only 1 out of 52 cards in there. Okay, that is a 2 of clubs. But notice here, when I go to find the probability for that 3 of hearts, there's still only 1 of them in that deck, but now the total's changed down here. There's no longer 52 cards in the deck anymore. Now there's only 51 because I've already taken out the 2 of clubs. So that's what this means over here. That's all that means. It's just when you go to find that second probability, just keep in mind the probabilities have changed. What's happened before it? Take that into account. How has things changed? Okay, and again, we got to multiply these 2 together. So 1 times 1 is 1. 52 times 51 will give us 2,652. All right, and rule number 3. This is the complement or not rule. The rule is basically we're just saying, I don't want this, I want everything else. For any event E, the probability of not E is 1 minus the probability it is E. Because again, I want anything else but E. Everything put together, as far as probabilities are concerned, everything put together is 1. So if I just want everything that's not E, all I got to do is take whatever E is and subtract it out. And that'll leave me everything that's not E. So the probability, for example, here, the probability of rolling a 3, 4, 5, or 6, the probability of rolling 3, 4, 5, or 6 is 4 out of 6, right? So we're looking at a die, right? There's 4 of these 6 numbers. So the probability of not rolling a 3, 4, 5, or 6 should be 1 minus the probability of actually rolling that. So I got 1 minus the probability. The probability of actually rolling at that was the 4 out of 6. And so the probability of not rolling that, I subtract those. 1 minus 4 out of 6 would leave me 2 out of 6. And if you reduce it, yes, that would be 1/3. So number 10. If the probability of red is equal to 0.34, what is the probability of not red? So again, to find the probability of something not occurring, we take the probability that it does occur and subtract it from 1. So the probability of not red would be equal to 1 minus the probability that it is red. Okay. So I know the probability it is red, that's 0.34, and I can subtract that from 1. So the probability that it is not red would be 1 minus 0.34 is 0.66. Number 11, the probability of someone choosing a red seat is 0.18. The probability of choosing a green seat is 0.14. And a blue is 0.21. What is the probability a student will not sit in a red or blue chair? Okay. So the probability they are not sitting in a red or blue should be 1 minus the probability that they are sitting in a red or blue chair. So I can figure out the probability they are sitting in a red or blue. Since it's an OR, we're going to be adding those two probabilities together. So I got 1 minus, so the probability of red is 0.18. The probability of blue is 0.21. Now just be careful, we want to make sure we add these two together first before we do the subtraction. So 0.18 and 0.21 give us 0.39. Then we'll come back and subtract that from 1. So 1 minus 0.39 gives us 0.61. So the probability of not red or blue is 0.61. Now be careful. Notice that is not the probability of green up here. The problem is if I added up 0.18, 0.41, 0.21, I am not going to get 1. So there are some other chairs in there aside from just green, red, and blue. So maybe there's a purple chair in there. So when I say not red or blue, I'm talking about it could be green or purple or yellow or whatever other chairs there are in there. So the probability for sitting in one of those chairs, that's the green, the purple, or whatever chairs there are in there, would be a probability of 0.61. All right, and rule number 4, conditional probability. A probability that takes into account a given condition. So here I'm looking at the probability of B given A. Now we've seen the given statement before, or we've seen this line before, given A in the compound event. This one's a little bit different. This is a conditional probability. We're looking for B that is inside of A. So there's a formula for calculating this. The probability of B given A is equal to the probability where B and A occur divided by the probability of A. Okay, so to figure this out, to remember the formula, it's real simple. You basically just take your statement here, stick an and sign between it, and divide it by the probability of the second one. And you notice that gives us our formula over here. So that's a quick little trick for remembering that formula. Stick an and sign between them, and divide it by the probability of the second one. And that would be your formula over there. Okay, so the probability of B given A, restriction of A, is equal to the probability of B and A divided by A. So let's go ahead and take a look at an example here. Number 12, in a recent study, it was found that the probability that a randomly selected student is a girl is 0.51. So a girl is 0.51. And the probability that a student is a girl and plays sports is 0.10. Girl and sports, 0.10. What is the probability a student selected plays sports if they are female? So I'm looking at sports if female. This is another word for given. So I want to write the formula and solve. So I'm looking at sports given female. So that would be probability of sports given female, and the formula would be, again, I'm going to stick that and sign between them and divide by the second one. So that would be the probability of sports and female divided by the probability of female. Now they give me the information here. The probability of sports and female, that's the girl and plays sports, is 0.10. That's the top part right here. The probability of female down here, a randomly selected student is a girl, is 0.51. So that's 0.51. So 0.10 divided by 0.51 gives us 0.19687 in the calculator. And again, we can kind of round that off and we'll get 0.20. So the probability that a randomly selected student plays sports, given they are female, is 0.20. So if we know they're female, what is the probability that they play sports? That's 0.20. Number 13, in a recent survey at Klein, it was found that the probability a student played baseball and soccer was 19.72, so baseball and soccer, 19.72%, and the probability a student played soccer was 53.52%. So what is the probability a student played baseball given they played soccer? So this one was kind of spelled out a little better for us. Baseball given soccer. Okay? And so now, they even wrote out the probability statement for us. Probability of baseball given soccer. So we're going to write out the formula. Right? And I'm going to abbreviate. Probability of baseball given soccer is equal to, again, you stick an and sign between them divided by the probability of the second one. So I got the probability of baseball and soccer divided by the probability of soccer. Again, they give us all the information here. The probability of baseball and soccer was at 19.72%, which I'm going to change back over to decimal form. So that would be 0.1972 divided by the probability of soccer, which is 0.5352. If I divide those out, I get 0.36846. And again, I'm going to round that off, and I'll get 0.37. If I needed to change it back to a percent form, that would be 37%. Finally, number 14, the probability that a randomly selected student plays sports if they are male is 0.31. What is the probability that the student is male and plays sports if the probability that they are male is 0.49? So I got a male is 0.49. Sports if, and again, that if is the key word for given. So sports given that they are male is 0.31. And this time I'm looking for the probability that the student is male and plays sports. So this one's a little bit different. Okay, with this one we're going to have to solve for something. So I'm going to write out the formula. So I'm looking at the probability of sports and male, sports given male is equal to the probability of sports and male divided by the probability of male. Well, I know the probability of male. I know the probability of sports given they are male, but this is the one I'm trying to find. So we're just going to plug in the information that I know, and then we can solve for that one up there. So I'm going to plug in the information I know. So the probability of sports given they are male is 0.31. The probability that they are male is 0.49. And we can solve this. To solve this, we're going to multiply by 0.49 on both sides. And those will cancel off. All right, and so that'll leave me 0.49 times 0.31 on that side. I can multiply those out, and that'll give me the probability of sports and male. And I'm going to go ahead and switch those around so that I got the probability of sports and male is equal to the 0.1519. And again, that rounds off. 2 decimal places would be 0.51 or 15%.